So we are primarily a computational research lab where, broadly speaking, we develop algorithms to help design both the body and brain of systems, particularly systems that can operate autonomously. So that includes robots, aerospace vehicles, could be even systems at a larger scale. Now, what do I mean by body and brain? By body, we specifically mean the physical design of the system, like component choices, the geometry, and so on, also called morphology. By brain, we mean the software running on the systems that allows them to decide how they want to operate in the real world. Now, in terms of brain, most of systems has different aspects like perception, control, planning. Our lab will mostly focus on kind of the planning level of the autonomy of the brain of the systems. For example, if you're thinking of UAVs, unmanned aerial systems, or drones flying, then the planning would be how to avoid collisions, right? How to get tasks done, how to work with other drones in that environment. So we operate kind of at the decision making at that level, not necessarily at the control level of how to fly. So that kind of summarizes what we do in the lab. So since we work on helping develop algorithms for autonomy, we also look at several real-world applications that kind of help us analyze how these methods would work and help society. So in the case of robots, for example, both aerial as well as ground vehicles, one motivating application that we look at is disaster response. So how do you search and deliver goods to victims after a flood, for example, or if somebody is lost or a vehicle is lost but is broadcasting a signal, how can you use the signal and have a team of drones find that vehicle or find the victim? So any sort of emergency and disaster response is a one big area of our applications. But that's not the only one. We also do aerospace applications. As an example, if you send a spacecraft in orbit, in order to protect the delicate electronics on the spacecraft, you have to make sure that it doesn't get too hot or too cold, right? So when the spacecraft is in the sun, it's hot, too hot. When it's in the shadow, it will be too cold. Now, in order to control the temperature inside, it needs to compute the temperatures that are occurring inside. That's easier said than done because computing a temperature profile is super expensive. So this is another work we did with NASA Jet Propulsion Lab, or JPL, to figure out how we can do these computations in a matter of seconds versus minutes. I think there are two very interesting directions of work that we are currently doing. I'll call them the work in coordination algorithms, that is algorithms that help coordinate multiple robots, multiple agents working together. That's one area. And the other area is in how to build trustworthy artificial intelligence by incorporating physics. So just to elaborate a little bit on the first area of work, essentially whenever you have multiple autonomous systems, for example, robots, drones, work together, you have to make sure that they don't have to take conflicting decisions, right? They can coordinate with each other to get the work done quickly. So in that area, we need algorithms that have to draw from various mathematical formalisms, right? So we build our algorithms by looking at not only optimization, but machine learning, graph theory, and so on. And it's a blending together of these different formalisms that allows us to build the decision-making capabilities for these systems that can provide planning within a matter of seconds, while also preserving the performance of this team of drones or robots over the mission scale. On the other side, the second kind of exciting area that I talked about was trustworthy AI. So trustworthy AI is being looked at from various directions. We approach it from this perspective of how we can incorporate physics to make AI more trustworthy. So kind of get the best of both worlds, right? Physics-based modeling is trustworthy, but could be very expensive, time-consuming, and so on. Whereas AI-based modeling could be very quick, but does not have the inherent trust because it could be black box. So how do you blend AI and physics so you can take decisions quickly or make predictions quickly for this kind of various aerospace or robotic systems, But at the same time, the decisions are trustworthy as opposed to being black box, something that the engineer or the user can trust. So I would say these are the kind of two major exciting areas of research in our lab. When we work on robotic systems, while we work on the planning level or high-level autonomy, we do have to work with other experts on the side of perception or control, because without that, we cannot actually deploy these algorithms either in simulation or in hardware, right? So pretty much every project that we work on, we work in tandem with, in collaboration with other experts. In some cases, these experts are external to University of Buffalo. For example, we work with audit experts at University of Texas at Dallas. We work with aerospace experts at NASA JPL and several small businesses in Western New York. While we also work with experts in various other areas of robotics at University of Buffalo, both in mechanical aerospace engineering and computer science. So I teach one undergrad course, which is called Applied Math for Mechanical and Aerospace Engineers. It mainly focuses on various types of numerical methods, building upon linear algebra, calculus, some amount of statistics. It's a required course for all mechanical and aerospace engineers. I teach a few different graduate level courses. A couple of them are in the area of optimization. One is more focused on classical optimization, like linear and nonlinear programming. The other one is focused on bio-inspired optimization, for example, genetic algorithms and particle swarm, which kind of draws from behaviors you see in nature and how you can use to build optimization algorithms. Kind of a newer course that I'm teaching over the last couple of years is called Learning for Autonomous Systems, where the focus is on how do you transition machine learning algorithms to make them work on complex engineering problems that have additional challenges or complexities that you do not see in other like vision or natural language type of problems. I feel my philosophy and approach to teaching has evolved over time with experience. So I would say now I prefer teaching to be more conversational, more interactive, as opposed to kind of a monologue. Obviously, that depends on the nature of the course. But what I mean by that is I like to stop and get feedback from the students, what they're understanding. I like to pose questions that makes them think about the topic that they just learned and can they apply it on like a scenario to kind of assess what message did I get across to them beyond just the math that we, for example, are learning. For us, it's very critical that the scientific developments that we are doing, we engage with the general public, and have a manner of messaging that we can pass on what's being developed and how it affects life and society going ahead. But beyond that, there's also an opportunity to kind of make the future generation, which is kids in K-12, aware of the cool things that we are doing and how they could be the ones doing and leading this kind of technology development in the future. So in that regard, I have been involved in a few things. For example, there's a Science Exploration Day that is organized in Buffalo in collaboration with UB, where they invite several topic experts to give a talk or presentation or demonstration. I was recently one of the invited experts a few weeks back, where I talked about how AI can be used to have multiple robots or agents work together. The research in the lab is primarily driven by students, mainly graduate students. So PhD students, I would say, take the lead in various research projects in the lab. So we have usually about 4 to 6 PhD students working in the lab. Each of them has their own projects. They often are the lead on various sponsored projects funded by federal agencies. And they closely work with master students, both masters in mechanical and aerospace engineering, as well as masters in robotics and computer science, who perform thesis research. Along with PhD and master students, we also have a rotating group of undergraduates who both gain experience in hardware and software, as well as contribute towards the research as they gain more experience. So we involve students at pretty much all levels at University of Buffalo to actually do the research, as well as in that process get trained in the various hardware software technologies that we work on in the lab. Not much. The one thing that I do on a regular basis is play tennis. So I play tennis about a couple times a week. I enjoy it. It's a taxing sport, but I love it. We play tournaments, and several of our colleagues here at UB also play with us in various teams. Beyond that, I play soccer once in a while, but that's pretty much it.